Good morning, everyone, or good night, good evening, wherever you are in the world. Thanks for joining for this early time. So I'm going to talk indeed about resolving the dust structures in AGNs using thermal infrared interferometry. There will be a second talk just after this by Almudena, which will also focus on the thermal infrared, of course, but on the slightly larger scales. So I will really focus here on interferometry with just a little bit of context so that you know what's happening. This work has been done over the last 10, almost 15 years, not only by myself, of course, but by very many people. I'd like to highlight the work of two former PhD students with whom I've worked a lot. That's Konrad Tristram, who's now in Chile, and Noel Lopez Gonzaga. Of course, also our supervisors, Klaus Meisenheimer and Walter Jaffe. And then also the current PhD students, Violetta Games-Rosas and Jacob Isbell, who will both talk after this talk. And many other people have helped in interpretation and discussing the results. All right, so let's start with the basics. This is a spectrum of two AGNs. One of them is a so-called broad line or type 1 AGN. It's the one with the blue line because it also has a blue appearance in the optical. So these are optical spectra. And the other one is a type 2 AGN. It only has narrow lines. And it has been, and still is to some degree, a riddle of why there are these essentially two classes of AGNs, one with broad lines, one with narrow lines. And of course, the view that has been brought up by Ski Antonucci and others in the 80s was based on then the observation of broad lines in polarized light. So that means broad lines that are scattered off from somewhere. The idea was then that you have some dusty structure around the center of your AGN where these broad lines appear. And if you look towards the center, then you see them as broad line AGNs. And if you look edge on, so to say, then you only see the narrow lines. This, I think, is known, I guess, by many people, but this is still good to go back to the basics. Then, of course, we have this picture that I'm still showing just because I'm going to deconstruct it, hopefully, in the course of this talk. So that has been the standard picture for many years. One might say perhaps not rightfully so, but nevertheless, it has been shown and is still shown in lots of talks. And this is really a PR picture. You can see this, for example, because the black hole actually has a little reflex here, which of course is totally unphysical. But nevertheless, this is a very popular picture. It has actually been clear from the beginning that it's not a physical picture, because at that time already, it was clear that a smooth, let's say dense dust disk around an AGN, as you can see here, would not survive for very long, because you would need really high temperatures to keep up, to puff this structure up to a scale that it can explain the type 1 and type 2 statistics. And at these temperatures, the dust wouldn't survive for very long. Then people have come up with a slight modification of this and packed the dust into clumps that help to overcome this temperature problem. You have essentially cool dust in the clumps, and these clumps are moving with respect to each other, and then you can puff up the torus without destroying the dust immediately. But then it's really unclear where does this puffing up happen, and why should it be a thick structure and not just collapse to a disk. The next iteration in torus models was then the hydrodynamical models. There's only a few in the world who do this, and I think one of the best ones that exist to date are from Koichi Wada in Japan. This is one of his models from already a few years ago, and this is just a zoom around the central region. I hope you can see this video that just shows a filamentary structure that appears after putting in radiation pressure well, also evolving the dust and gas there in a hydrodynamical way. There have been other simulations as well, also by Koichi Wada and by Mark Schartmann and a few other people, to try to relate the physical properties of the AGN with what is happening in these outflows. And one of the interesting predictions that may perhaps have been discovered now in observations as well, is that you would expect, depending on the Eddington ratio, a different, let's say, torus structure, a different structure of the central region. So you can see at lower Eddington rate at the bottom of the figure, you can see a more compact region perhaps, or a less turbulent region. And at a higher Eddington ratio, this whole region is puffed up more. You can see the disk is a little bit thicker, but it's still very complex, and it's hard to make a clear-cut prediction. We would really like to have more models that actually make these predictions between Eddington ratio and outflow, for example, or accretion, efficiency, and torus structure, or also related to the nuclear star formation, because we know that many of these galaxies have very strong ongoing or just recent star formation. So potentially that is also a driver there. So how does that look like then in the mid-infrared? There has been this wonderful collection by Daniel Asmus, who took all the high-resolution 8-meter class images that existed in the world and re-reduced them and calibrated them carefully, and has made this atlas of, I think, 300 or so objects. And what you can see there, I think Almudena will highlight more of this, but you can see immediately that most of these sources are essentially unresolved with 8-meter class telescopes. You can still do a few things with these unresolved objects. You can do SED modeling. You see, for example, that the thermal infrared is really where the action is happening. Almost the peak of the SED is in the thermal infrared. The region at 20, 30 microns is not accessible from the ground. So that makes it difficult, but in the thermal infrared, let's say 3 to 20 micron, you really look at where these things are happening. You can try to constrain torus models with this that have these clumps around the center, and you have an inner radius, an outer radius, an opening angle, inclination, and so on. And there's one really interesting result that came out of this, but I'd like to also be, I think we also need to be cautious with this, and that's from Cristina Ramos Almeida, who found that the number of clumps and the half opening angle that you find with this torus modeling is actually higher in type 2 AGNs. So as you might expect from just a naive way, and that is actually what they find from these SED modeling. But this uses essentially the old view of the AGN torus, so this toroidal structure of clumps, and that's how they find this. So if we want to see what the structure actually looks like, we see that the resolution of a single telescope is not enough. So if we have an 8-meter telescope at 10 micrometers, this gives us a resolution of 300 milliarc seconds. With or without AO, almost doesn't make a big difference. If you have a good night, you essentially get that resolution. But that is not enough. So what we need is more telescopes, and that's of course interferometry, where the resolution is actually given by lambda over 2D. So you gain both by the large separations of the telescopes, and since you only probe the largest spatial frequency, namely between the two telescopes, there's another factor of 2. So you actually, for the same, let's say for an 8-meter baseline, you already have twice the resolution. That's also why aperture interferometry is better than, in resolution terms, better than just normal imaging. And there's been a lot, there have been a lot of results with infrared interferometry in particular. I produced this overview a couple of years ago for a review paper where I think I compiled all papers that have ever been written on infrared interferometry of AGNs. You can see that the majority of results at that time has been obtained with MIDI, so the mid-infrared interferometer at the VLTI. It has been decommissioned in 2015, I believe. And a few results, especially in the very early days, have also happened with the Keck interferometer and the near-infrared. And then there was one result with Vinci by Markus Witkowski, who talked yesterday. And there was one result with Amber, also near-infrared interferometer at the VLTI. Since then, of course, the major thing that happened was the gravity came online. So there were a few more results from archival data from MIDI. These are also quite noteworthy by Walter's PhD student, Noel Lopez Gonzaga, who looked at mid-infrared variability after X-ray variability in our most famous source, NGC 1068, and didn't find a change in the mid-infrared. And then 2 papers by James Leftley, who is now a postdoc with the Nice interferometry group, with the MATISSE interferometry group in Nice. And then gravity came online, the near-infrared interferometer that uses all 4 telescopes, that has very high sensitivity because it can use one source to fringe track and another source to actually take the observations, or it's just generally very sensitive. And there's some really spectacular results, especially the rotation of the broadline region in 3C273, and also the image of the dust sublimation region in NGC 1068. These are really very fascinating results. I'm not going into more details here because that is near infrared and we wanted to focus on the mid infrared in this talk, but I'd like to recommend to check them out if you haven't seen them yet. Okay, so with so many results, we need a little bit of an overview, and that's actually not hard to do because among all these sources that have been observed with METIS, two sources very clearly stand out, and that's the Cerseinus Galaxy and NGC 1068. They are by far the brightest sources, and then the other sources are really a factor of 10 fainter and are essentially at the limit of what METIS could always do. And so for the remainder of this talk, I'm going to highlight in a couple of minutes each the Cerseinus Galaxy and NGC 1068, and then say a little bit more about the sample statistics. All right, so the Cerseinus Galaxy has probably been studied the most. It's probably the AGN that has been most studied, or where most telescope time from METIS has been spent on. And this is because, as you've seen, just it's one of the brightest sources, and also it is located at a very favorable declination of well, minus 65 degrees. That means it makes these wonderful, almost circular tracks in this so-called UV plane. So that's the plane of how the telescope separation would be seen by the object, so to say. And whoever is not muted, perhaps mute, so that we don't hear the breakfasting. And in this plot, made by Conrad this time, you can see plotted here the correlated flux. So that's essentially the level of unresolved flux that remains at a certain baseline. So think of the baseline as a resolution, and the angle is just the position angle on sky. And you can see immediately from this plot that there are some there are some regions, like in the lower left and in the upper right, where on the largest baselines, the correlated flux is increased a little bit. And that means that on these baselines, the source is less resolved. So you have more unresolved flux, and that tells you that along this direction, you have a very compact direction. So this already tells you that there must be something that is elongated to the, let's say, upper left, lower right, a disk on the smallest scales. And then you can see a similar behavior on the shorter baselines, which tells you the same, but in the opposite direction for the smaller scales. And this can be put, of course, in an image. And that's essentially what comes out here. So there's three components that we see from the mid-infrared interferometry in this image. There is this green-purple gradient blob, let's say. This is where the majority of the emission, 70% or so in Cerseinus, is coming from. And curiously, that has been seen since, well, a bit before 2014 perhaps, but we never really understood how to interpret it. That is not in the direction where we would expect it, right? So this torus image that everyone has in mind is there is this donut-like structure that is in the plane of the galaxy, and perpendicular to it, you have the outflow and the radio jet and everything. But no, we see most of the emission actually in the direction of the outflow cone, which is indicated here in cyan lines as ionization cone. And then there's a second component, which is perpendicular more or less to this outflow. That's a very thin disk where the minor axis is actually unresolved. So it's an upper limit. And this is coincident with a disk of water masers, 22 gigahertz maser, water masers that are seen with VLTI. And we don't have absolute astrometry, so we don't know if they're really coincident, but since they have the same position angle and are also not too different in size, factor 2, we always plot them on top of each other. So we think that this disk component is, let's say, the dense midplane, which is actually very thin, like the maser disk. Maser disks are always thin. You only see the emission in the midplane. And the big emission is really dust that is in the outflow cone. And what exactly that means is still a bit unclear. I think there's a third component here, which is a point source that you can see on top of the maser red part that was required to have a good fit to all these visibilities that we got at the time. I think that this already an indication that there is a more complex structure in there. So of course, this is not just two blobs, but there is a more complex filamentary structure, as you have seen before in the simulation by Keiji Wada. But we can also try to model this already, and that has been the PhD thesis by Hans-Uli Judt, supervised by Mark Schartmann in Australia at the time. And he explained actually this maser disk with this extra knot in there, with this extra point on the red side of the maser disk, as a warped disk, where you kind of see towards the knot of this warp exactly at the position, or where you look at this knot, so to say, you see you have a larger viewing line towards this tilted disk, and therefore you see more emission there, and it's brighter there. All right, so there is this correspondence between these two. Yeah, so that's essentially what we know from the Cerseinus Galaxy, right? So we have decomposed the central emission into a large outflowing part and a compact disk that is potentially coincident with the maser disk. Now in NGC 1068, I'm not going to talk too much about it because actually that's the talk of Violetta, but just I wanted to highlight and bring up this picture again that has been mentioned by Uli Käufl yesterday in his history talk. So that's actually the first high resolution image of NGC 1068 taken with the Miracle camera at UCURT. So there was an MPE and Edinburgh collaboration with actually a field of view that is the same as METIS has, so 10 arc seconds, but very, very fewer pixels. So it was, I think, 50 by 50 pixels or so. They directed it towards NGC 1068, and you can see the image is from this camera, and the contours are from the O3 emission taken with the Hubble telescope. That has been done later again with the Keck telescope, with the Merlin instrument there. Of course, 8 meters, so twice the resolution and also more sensitivity, but not to extended emission, as we know. And you can see that, well, there are some differences, let's say, between these images. I would actually be curious to discuss this with whoever has been involved in these images, if they believe that is a good match or not. So the decomposition that has been done with the Keck telescope, which is still, as far as I know, the best image that we have at 8-meter class, actually sees a core and what they call a tongue to the north, and another southern blob to the south of the core. It's not quite coincident with what we have in this very first image. All right, and on top of this, we can plot what METI has found. You can almost not see it here because it's super, super tiny, but you can perhaps see these 3 small red ellipses if you look very closely. There's a very small ellipse at the center, which is essentially, we think, again, the disk. It's also coincident with the maser emission. And then there are 2 other blobs which we couldn't fully locate at the time. Yeah, so we essentially also decomposed this into a bit of an image, but there is certainly more complexity there going on. And we're getting a glimpse of the complexity now with MATISSE already. This is, as I said, will be summarized, shown by Violetta's talk later this morning. And this is the first L-band not reconstruction yet, but a model image again with 2 Gaussians. I can zoom in a little bit before it was the actual size. And you can see that in the L-band, we seem to see also 2 hot components that then can be compared again with gravity. This is the gravity image that I mentioned before. They actually do an image reconstruction, and they find quite a number of sources. And we can discuss perhaps later if there is a correspondence or not. All right, so these are the 2 best sources. You can see that it's still pretty basic what we find. So we can decompose the emission into a few blobs, a few elongated blobs. We can try to correlate it with other structures seen with VLTI, but we can actually not do much more yet. This is coming. So let me talk for a few minutes about the sample that we have. So the
5 minutes, Leo.
Thanks. The largest sample that we were able to collect so far was from a METI large program on which I worked in my PhD thesis. So that's some time ago, but it's still almost the largest sample that we have here. And this is looking at the half-light radius for all these AGNs. What you can see here is that in the near infrared, these are the yellow and green points, there is roughly a correspondence between the radius and the luminosity in the expected way. So the radius increases as the square root of the luminosity, as you would expect from a centrally heated source. In the mid-infrared, there is also this kind of trend, but it's by far not as clear. And there's also no difference between the type 1 and type 2 sources. What we can say is that the mid-infrared emission starts essentially in most sources at 4 times the inner radius. That's the most compact sources we see. And it's never more extended than 20 times the inner radius. We can also look at the level of unresolved flux and compare this to models. So at the left, you see what models would expect in terms of visibility at the longest baselines. And you can see that no matter how you turn this torus, you always expect essentially the same visibility of, let's say, 20, 30% or so, a bit dependent on inclination angle, but not so much on position angle. But what we observe to the right is actually a huge variety of unresolved fluxes at the largest baselines for all these sources, between 20% and 100% for the fainter sources. So that tells us that these tori are not the same. They're all different. All right, the other thing I'd like to highlight from the sample statistics is the elongation. So for a couple of sources, we can do what we did in 1068 and in the Cerseinus Galaxy. So look at the elongated emission, constrain the properties of an elongated Gaussian, so the axis ratio and the position angle. In 1068, we have seen that the elongation is closer, but not identical to the optical polarization axis and the ionization cone. So it's polar elongated. And this has since been done with a couple more sources. And all the sources where we can determine the elongation have their major axis much closer to the outflow than to the orthogonal direction. So this really led to the new view, let's say, of the AGN torus, that the image on the left is really not what you should take anymore. A much nicer sample, a much nicer picture that has been produced by Sebastian Hönig is seen, you can see on the right. And this is really how you should see it. So there is this dense disk in the center where most likely most of the near-infrared emission is coming from, probably also the L band, 3 to 5 micron emission. But the 10 micron emission is really dominated by the outflow cone. And whether this is dust that is lifted up from the center or whether it's dust that has always been there from the galaxy and is just illuminated or perhaps entrained by the outflow that is happening in molecular gas, that we still don't know. We don't have kinematics, but that's certainly the summary picture. All right, one last summary, one last statistics slide. This is a recent result by James Leftley. Very interesting result, I think. I think it definitely needs follow-up and more observations. James compared the level of the extended emission with the Eddington ratio of the AGN and found a correlation that is significant within the sources that he had. Of course, there's a huge uncertainty with the Eddington ratio, with the black hole mass that goes into there. But it seems that the sources are larger or have more flux in their extended source and their extended component if they have a higher Eddington ratio. And that can be interpreted in the sense that higher Eddington ratio means more radiation pressure. So that means the sources are really puffed up by radiation pressure. That is
1 minute.
Thank you. All right, so we clearly need more sources, and this is the second talk I'd just like to highlight here. Jacob Isbell will give a talk later this morning as well. He went through the entire archive of ISAC observations to look for sources, because as you can see, or as you saw before, we are really very much sensitivity limited with interferometry, and we need the resolution of interferometry at this time at least. So with this huge sample that he built up, he do some interesting physics by himself, but we will also be able to select a few more sources to study with MATISSE. And just to give an outlook, this is what my PhD supervisor, Klaus Meisenheimer, did at the time. He was originally a radio astronomer. So he compared the evolution of infrared interferometry with radio. You can see in the radio, it took quite a while to go from individual blobs to detailed images. And this is perhaps where we're at right now. You see MATISSE, well, it wasn't quite 2018, but 2020. We're hopefully getting there within a year or so. But not quite yet. All right. The one last minute on the
very short minute, please.
A short minute. Okay.
Yes.
So this is just putting together results from different studies. Again, I won't talk about the larger scales because Almudena is going to do this, but I'd just like to highlight that METIS will really be the instrument in the coming years to study these polar outflows. It's in terms of its resolution, it's perfectly suited to resolve the extended emission. It has just the right spatial resolution, high enough that it can see it, but also not like interferometry, too low sensitivity that you're losing sensitivity for sources. So this is what we expect to see with METIS. And actually, at a recent AGN conference, people were asked, what do you think is the single most fundamental missing future observation? And 53% said high sensitivity mid-infrared observations with an IFU, which is exactly what METIS has. All right, a few people also were pessimistic because they need more models. All right, I'll leave you with my summary. So mid-infrared interferometry, we resolved about 30 AGN tori to date. We know they're all different, so there's no unified model in that sense already. We also know that most of the emission is towards the polar direction of the AGN, so towards the outflow. So don't think of the donut emission. And in the future, especially METIS, in the near future MATISSE, and in the long-term future METIS, will certainly give us more insights on this. Thank you.
Thank you very much, Leo. I miss the applause in these online conferences. So this has been a great review, and I've learned a lot. So are there any questions? Please remember the AGN Galaxy Slack channel for the questions, and I will also try to keep simultaneously an eye on raised hands. Don't see any raised hands. Let's see on the channel. So here we have the first question from Josef Varga. Is the new view on AGN structure in agreement with the optical observations of the broad line and narrow line region? Actually, I also wondered, where do you fit in the broad and narrow line region now in Sebastian Hoenig's model?
Yeah, that's a very good point. So of course, you still need this, geometrically thick structure to obscure the broadline region for the type 2 AGNs. The idea in this new model is that you have that this is happening essentially at the smallest scales. So not at the parsec scale where the mid-infrared emission is coming from, but really more or less at the sublimation radius, where perhaps you even have a puffed up inner structure like in protoplanetary disks, which is why I think we should discuss tomorrow more about the relation between these two subjects. So you might not just have a thin disk that we have seen from the MIDI images, but the thin disk might in the very center be puffed up. So yeah, you have a higher geometrical thickness to block the light. And then this would still be in agreement with the optical observations.
Okay, thank you. Another question is from Valentin Ivanov. Wouldn't the James Webb help you more with the sensitivity? And so the big question, what is more important, sensitivity or angular resolution?
Yeah, that's also a really good point. I think for the polar outflow, we mostly need, we need both, right? I mean, we need enough sensitivity, of course, to see them, but that has, I think, not been the problem with Vizier. I think Vizier was sensitive enough to see the polar outflow in the sources where it could resolve it, but it needs higher angular resolution. So with METIS, we will be able to resolve it, and it will certainly be sensitive enough. I mean, I showed this this image here of the simulations. Where is it? This one here. So this is what we expect actually within just a few minutes with METIS. So we will be able to resolve the structure and get actually really fancy images with METIS. With James Webb, I think we will, of course, we will be much more sensitive, especially to low surface brightness emission. So James Webb will be excellent to do the polar emission on the larger scales to see how it really extends, because with METIS and interferometry, we've only seen the polar emission in the very center, where the surface brightness is high enough that we can observe it from the ground. And should this polar elongated outflow be actually larger, say not just 50, 100 parsec or so, what we can see from the ground, but perhaps even up to a kiloparsec. For that, we certainly need James Webb.
Great, thanks. So last comment, maybe very brief comment here from Lei Chen about the near-infrared and mid-infrared size of tori. I want to point to the fact that protoplanetary disks have similar behavior. They have similar near-infrared size after normalized with with square root luminosity, but are diverse in mid-infrared size. Could be related to diversity in radial disk structure, gaps mainly. So that's quite a comment.
That's a very good comment. I mean, I know by, for example, John Monier's paper where he does a similar plot for the protoplanetary disks. What I don't quite understand from the protoplanetary disk folks, but perhaps we can indeed discuss this in the Slack or tomorrow, is that the protoplanetary disks don't seem to be dominated, the mid-infrared emission doesn't seem to be dominated by the outflow. So why do they have this diversity in the end band emission? It must be a different reason than for us.